Okay, everybody. I want to make one more video for Unit 7 and just kind of discuss the last part of Unit 7. So let's make sure we understand what we need to be able to do in Unit 7 so far, and then we'll talk about the last part of it. So Unit 7 is about reaction rates. So different things you want to be able to do. If given the rate of disappearance of a reactant, use stoichiometry to get the rate of formation of a product, or sometimes it might be called the rate of appearance of a product, or the rate of disappearance of another reactant using the stoichiometric ratios. Right. So if you're given the rate of appearance or disappearance of one thing or another in the reaction, all you have to do is multiply by the mole ratio and the reaction, the coefficients, and to get the rate of disappearance or appearance of the other thing that you're asked about. All right, so that's number one. Number two is the differential rate laws and the integrated rate laws. For the differential rate laws, the rate equations, you'll be asked to write the rate equation for a reaction. And so that will always be rate equals K, and then times the concentration of each reactant raised to its order. Sometimes it might include a catalyst if it's a catalyzed reaction, but if not, just the reactant and raised to each order. Remember, those orders are going to be 0, 1, or 2. And you'll have to figure that out based on experimental data. And the way we've talked about it so far is, you do different trials of that same reaction with different amounts, and you look what happens to the rate. If I double this and the rate doubles, it's first order. If I double this and the rate stays the same, it's 0 order. If I double this and the rate quadruples, it's second order, right? So that's one way to do it. And today I'm going to show you the other kind of experimental data you can use to figure out if you have a first order, a 0 order, first order, or second order reactant, which we're going to talk about in a second. Then, being able to solve for K, getting the units of K, and then using the integrated rate laws, knowing which integrated rate law is the one to use. If you're 0 order, then it's just the concentration rate law. If it's first order, it's the natural log of the concentration rate law. And if it's second order, it's 1 over the concentration rate law. And remember that T1/2 equation, the half-life shortcut equation that's on your formula sheet, that's only for first order kinetics. And you want to remember that if you're asked about radioactive nuclear chemistry, radioactive decay half-lives, if that's what you're talking about, that's always first order kinetics, so you can use that shortcut. The other thing you want to know about reactant orders is how it relates to half-life. And this is going to go hand in hand with what we're going to talk about today, which are the different graphs you might get to determine if something's 0 order, first order, or second order. But just remember, if you're 0 order, your half-life's going to get shorter and shorter and shorter. So if the first time it cut in half, it took an hour. The next time it cuts in half, it's going to take 30 minutes. And then the next time it cuts in half, it's only going to take 15 minutes. And then the next time will be, 7.5 minutes, and so on. So the half-lives get shorter and shorter if you're 0 order. If you're first order, the half-lives remain constant. Okay? So it always takes this amount of time for the amount to cut in half. So to go from 100 to 50, if it takes an hour to go from 50 to 25, it's going to take another hour. And then to go from 25 to 12.5, that's going to take another hour. If the half-life stay constant, that's a sign that you have a first order reactant or reaction. And then for second order, the half-lives get longer and longer. So if the first time it cuts in half, it takes an hour, it's going to take 2 hours to cut in half again. And then it's going to take 4 hours to cut in half another time, and then 8 hours, and so on. So the half-lives get longer and longer if you're second order, okay? So let's talk about the graphs, all right? So I'm gonna go to the paper here, and let's look. Okay, so these graphs haven't really come up in a long time, but it would be, this should make sense to you These graphs show rate versus concentration. So if you adjust the concentration, what happens to the rate? And what this graph is showing you is that as we increase the concentration, the rate stays the same. So if you graphed rate versus concentration data and you got a straight horizontal line, that would be a sign that you have a zero ordered reactant, right? But if you didn't get that, if you graphed rate versus concentration and you got a straight line, a positive sloping straight line, then that would show you its first order, because whatever change you do in concentration, the same thing happens to the rate, and you're going to get a constant slope there, okay? But if you graphed rate versus concentration and you got kind of like an exponential line, that would tell you it's second order, all right? Okay, so again, I haven't seen these in a long time. This is just making sure you understand how, depending on what order you are, second order, first order, or zero order, how you change the concentration, how does that affect the rate, okay? And so we know that second order, whatever we do to the concentration, the same thing happens to the rate squared. First order, whatever change we make to the concentration, the same thing happens to the rate. And then for zero order, whatever we do to the concentration has no effect on the overall rate, okay? So that's number one. Now, the next thing I want to show you are the graphs that will show up, and you need to know what you can get from the graphs. So this goes hand in hand with the integrated rate laws. All right, so let's say you're given concentration versus time data. And now I really should say amount versus time data, because if you're given, you know, a lot of times you're given concentration versus time, and that's easy, because the integrated rate laws, if you look at them, the integrated rate laws use the brackets notation. So technically the numbers you're supposed to plug into the integrated rate laws are molarities, or concentrations, okay? So, you know, the thing you want the most when studying kinetics would be concentration, molarity versus time data. But sometimes on the AP exam, you'll be given absorbance versus time data, or partial pressure versus time data. And understand that the absorbance is directly proportional to concentration, and also understand that partial pressures of gas would be directly proportional to concentrations. So if you're given molarity versus time data, or absorbance versus time data, or partial pressure versus time data, you can figure out the reactant order based on making three different graphs, okay? And these are the three different graphs. And so I know it says concentration of A versus time, but it could be, this could be absorbance of A versus time, and it could also be partial pressure of A versus time, okay? So the three graphs you're gonna make, okay, so if you're given amount versus time data, and the different amounts could be, you know, hopefully it's concentration, but if not, it could be absorbance or partial pressure versus time data, you would make three graphs. And what you're gonna be looking for is which graph gives you the straight line. All right, and I'm going to show you what I mean by that in a second, but let's just make sure we understand. If I'm given concentration versus time data, all right, I'm looking for which one of these graphs give me a straight line. So I could make the molarity versus time data. So molarity on the y-axis and time on the x. The next graph I'm going to make is the natural log of the concentration versus time. So I would put the natural log of each concentration on the y-axis and time on the x. And then the last one I would make is 1 over concentration versus time data. And 1 over concentration would go on the y-axis and time would go on the x-axis. So notice how they kind of correlate with the different laws. This would be the zero order integrated rate law. This would be the first order integrated rate law. This would be the second order integrated rate law. So here's the deal. If this gives me a straight line with a constant slope, then I'm zero ordered. But if it doesn't give me a straight line, then I would look to one of these two. One of these graphs is going to give me a straight line, but only one will. So if this doesn't give me a straight line, then maybe I go to this. And if this gives me a straight line with a constant slope, then I know I'm first order. But if both of these don't give me a straight line, then this one needs to. And if this is the one that gives you a straight line, then you know you're second order. So let me show you what I mean by that, right? So you make 3 graphs. Whoops, that's not what I wanted to do. I wanted to zoom in. Can I zoom in? All right, there, okay, sorry. All right, so let's say you're given concentration versus time data and it's 0 order. If you made those 3 graphs, notice the only one that gives you the straight line is the concentration versus time. You get a straight line, okay? Natural log of concentration versus time gives you a curved line like that, and 1 over the concentration line gives you a curved line like that. So this is the only one with a constant slope. Okay, so now also understand that the slope of that line, if this graph gives you the straight line, then you know you're 0 ordered, and the slope of that line, if you flip the sign of the slope, it's going to be the rate law constant. All right. Now, if you're first order, then that concentration versus time graph is not going to give you a straight line, but the natural log of the concentration versus time graph will give you a straight line. And notice 1 over concentration versus time doesn't give you a straight line either. So the only one that gives you the straight line there is the natural log. So if this is the graph, the natural log versus time, if that's the graph that gives you the straight line, then you know you're first order. And again, if you calculated the slope of that line, you flip the sign, that would give you your rate constant. All right, and then again, the last one is natural log, or not natural log, 1 over the concentration versus time. So notice here we had a second order reactant. Concentration versus time did not give us a straight line. Natural log of concentration versus time did not give us a straight line, but 1 over concentration versus time did give us a straight line. Now notice this time, when it's the 1 over, you get a positive sloping graph. So the slope of that line is the rate constant. You don't have to flip the sign, okay? But another thing I want you to understand is you don't have to just do this with concentration data. This could be partial pressure versus time, natural log of the partial pressure versus time, 1 over the partial pressure versus time. Whichever one gives me the straight line is going to tell me the reactant order. And then the slope of that line is going to give me the rate constant. Okay? And the other one that you could use is absorbance. Absorbance versus time. Natural log of absorbance versus time. 1 over absorbance versus time. What I want you to not think you have to do, I don't want you to think you have to do this. If you're not given concentration versus time data, instead, if you're given partial pressure versus time data or absorbance versus time data, don't think to yourself, oh no, I need to know molarities. So figure out how to turn your partial pressures into molarities, or use Beer's law to turn your absorbance values into molarities. You don't have to do that. Just use the absorbance values and as if they were concentration values, or use the partial pressure values as if they were concentration values, because they're directly proportional to the concentration. So they're going to make the same types of graphs. They're going to behave the same way. So you can just use those amounts. You don't have to do any kind of conversion. Okay. So hopefully that makes sense to you. I want to show you a couple of examples, all right? So these are from, release tests and practice tests. So if you've done some of the practice tests, you've probably seen these. But again, first off, yeah, okay. So this is one of your handouts, but we've kind of talked about it already. So let me show you, okay? So here's a sample question. This was on one of the online practice tests that you have, the 2019 practice test that's in AP Classroom. This is question 13 on the multiple choice. And what I want you to notice is, hey, they gave us concentration time data, natural log of the concentration time data, and 1 over the concentration time data, right? Did they give us a reaction? No. So they didn't, well, let's see. Nope, okay. So that's all. That's all this question is. And we want to know what would be the rate law of the reaction. So we want to know, is NO2 0 order? Well, notice that that's not an option, okay? Because we don't have rate equals K and that's it. So we know it's not going to be 0 order, but based on the answer choices, but let's try to figure that out. Is it going to be zero order? Is it going to be first order? So that's my rate law. Or is it going to be second order? So that's my rate law. So hopefully you understand that you can cancel out C and D because rate laws don't look like this, all right? So it's either A or B. Now, the question is, which one of these would give us a straight line, okay? And unfortunately, we don't have the data to get half-lives because like if at time initial, 0.5, what's half of that? 0.25. We didn't make it down to well, I guess we did make it down kind of in between there, but we don't have enough data to get a second half-life. So I'm not going to be able to determine based on half-life. So what you're going to do is, which one of these is going to give you a constant slope? Because a constant slope would be a straight line. What you would do, well, we know it's not this one, but what you would do is say, okay, well, the time values here are increasing in the same increments. 100 seconds, 100 seconds, 100 seconds. So to have a straight line, we need this to decrease or this increase at a constant rate as well, okay? So if we go from 0 to 100, here we're going from 0.5 to 0.36. And then as we go 100 to 200, we're going from 0.36 to 0.28. That's not the same difference. So let's go over here. From 0 to 100, we go from 0.69 to 1.01. But then from 100 to 200, we go from 1.01 to 1.25. From 200 to 300, we go from 1.25 to 1.45. Again, that's not the same difference, okay? But if we look here, as we go from 0 to 100, we gain 0.75, 2 to 2.75. And as we go from 100 to 200, we gain another 0.75. We go from 2.75 to 3.50. And then as we go from 200 to 300, we go from 3.5 to 4.25. That's another gain of 0.75. So this is increasing at a constant rate at same constant intervals increase. So we know that this graph, if I graph natural log, 1 over the concentration versus time, that's going to give me a straight line. That means it's second order, so I know my answer is B. Okay? So first I want you to understand how we'd have to do that. And remember, you don't have a calculator, so you're going to have to be doing this in your head, or you can write on the test so you can kind of map it out and do the math quickly. But that's what we would have to do. Understand that if we wanted to take a shot in the dark, if we wanted to guess, hopefully we're smart test takers in that we could cancel out C and cancel out D, because rate equations don't look like that. Okay? All right. But the other thing I want you to understand is they could easily have given you absorbance, natural log of absorbance, and 1 over absorbance, and done the same thing. And you don't have to change it to concentration. What you would be looking for is the exact same thing that this chart gave us. And the other thing they could do is partial pressure, natural log of the partial pressure, and 1 over the partial pressure. Okay, so understand you could see something straight up concentration. It could be absorbance. It could be partial pressures. Just treat them the same way. Treat them the same way. Okay? All right, so let's look at another one. All right. So what I want you to realize real quick, before we even read the question, concentration versus time did not give us a straight line. So we know it's not zero order. We know it's not zero order. We know it's not zero order. So concentration versus time did not give us the straight line. So that means either this plot has to give us a straight line, the natural log of concentration versus time, or 1 over concentration versus time has got to give us a straight line. And we know if that gives us the straight line, then the magnitude, that means absolute value of the slope, is the K value. And if this gives us a straight line, the magnitude of the slope is the rate constant. So here is where I want you to understand it. We can see that the half-life remains constant. So to go from 1 to 0.5, it took 20 seconds. And then to go from 0.5 to 0.25, it took another 20 seconds. And then to go from 0.25 to 0.25 to 0.125, it took another 20 seconds. And 0.125 to, what would that be? 0.125, 0.0625 took another 20 seconds. All right, so what happened? The half-life remained constant, first order, so the answer is A. Okay? But this could also have been partial pressure versus time, and then the natural log of the partial pressure, or versus 1 over the partial pressure, or absorbance, same thing. Okay? All right, so this next one, I want to show you 2 examples. Okay? All right, so this one is a little bit weird, but what we should understand is we know it's not zero order, because so each time increment is an increase of 200 seconds, right? 200, then another 200, then another 200. But a decrease in concentration isn't the same. 0.7 to 0.1, okay, what is that? 0.6, but then 0.1 to 1.7, that's 0.4, and then 1.7 to 1.3, that is, 1.7 to 1.4 is 0.3. So we're not decreasing, this isn't decreasing at a constant rate. So if we graph the concentration versus time, we wouldn't get a straight line, okay? So we know it's not zero order. But what I want us to focus on is question number 27. Which of the following statements is correct interpretation of the data regarding how the order of the reaction can be determined, okay? And this is one where we're gonna have to use we know it's not zero order, but I don't think any of the answers talk about zero order. So it's either first order or second order. It could be second order because the coefficient's 2 here, but we don't know. We don't know if this is a one-step process. So if it's not a one-step process, it has a different mechanism, then this could be first order as well, all right? So the reaction must be first order because there is only one reactant? No, that's not true, okay? The reaction is first order if the plot of natural log of concentration versus time is a straight line. That is true. So go ahead and select B, but let's read C or D. The reaction is first order if the plot of 1 over concentration. No, it would be second order if 1 over concentration. And then the reaction is second order because 2 is the coefficient. Don't fall for that trap. We weren't told that this happened in one step. If we were told this happened in one step, then boom, D would be the right answer. But we don't know. We weren't told that. And we weren't told that in any part of this question. So this one is just the only one that is true is B, okay? But on the same test, on the free response, I want to go to one where you're instead of, so what I want you to notice is here we were given absorbance versus time, okay? Not concentration versus time. So if, in this question, we got the molar absorptivity constant, right? If we made the graph and found the slope of it and got the molar absorptivity constant, then maybe we could get concentration values here and that kind of thing, but we don't need to do that, all right? Treat absorbance like you would concentration to directly proportional. And so what I want us to understand is how to answer F. Explain how the experimental data indicate that the reaction is first order. So they're telling you it's first order with respect to this. So they're telling you that reactant is first order. And this is measuring the absorbance based on this reactant's concentration. So there's 2 ways to go about this. But understand you're under a time crunch. So maybe somebody's first inclination would be to make the 3 graphs, right? What you could do is say, you could show that because it's first order because they're telling you it already, you could say, okay, well, the natural log of absorbance versus time graph gives you a straight line, but you would have to show that. So you'd have to take the natural log, and remember, you have a calculator on the free response. So the natural log of this, the natural log of this, the natural log of this, the natural log of that, the natural log of that, and then graph those numbers versus time. And you would have to sit there and make the graph, okay? And show that it's a straight line. But the better way, the faster way, is look for half-lives, okay? If you do 0.782 divided by 2, that's around 0.389. And if you do 0.389 divided by 2, that's 0.194. So the first half-life took 3 minutes. The second half-life took also 3 minutes. Therefore, it's first order. And that's the explanation. That's the first explanation they were looking for. And again, you don't have to change this to concentration. And this could have also been partial pressures. But real quick, let's show you the answer key to that and show you the explanation. Is it? Okay, so here it is. Absorbance is proportional to concentration. Absorbance is halved after 3 minutes, and again after another 3 minutes. Thus, the half-life of the reaction is constant, so the reaction must be first order. There you go. You got it. Okay? Or you could have made that graph. But what's going to save you more time? This. All right, so understand how the half-lives work. Look for that. You're probably most likely, I won't say never, but more than likely, you're not going to actually have to graph stuff on the AP exam because it's too much time, and there's an easier way to do it. There's a shortcut. All right, so that knowing how reactant order and half-life connect is that shortcut for kinetics. Okay, all right. So that's it, right? That's really what you need to know for kinetics for the AP exam and your final exam. So Unit 7 in the bag, all right? So we will be reviewing from here on out, and that's not a long time. We only have 3 more, including today, 4 more class periods until your final exam, and then your AP exam. So anyway, hopefully you found that helpful. And yeah, have a good one.